Alright friends, welcome back. In this video I'd like to go ahead and start Chapter 3 of our textbook, and Chapter 3 is going to discuss polynomials. So here in the first video of Chapter 3 we're going to take a look at one of the more simple types of polynomials, which is your family of quadratic functions. And I know that that's something that you've probably seen in a few algebra classes before now, but in this video I just want to go ahead and make sure that we cover a brief overview of what quadratic functions are, and as well as take a look at a bunch of the characteristics of their graphs and just make sure that we know how to analyze the graph of a quadratic. So let's first go ahead and define what a quadratic is. So it's any function that looks like what you see here. F of x is equal to ax squared plus bx plus c, where a, b, and c are just simply real numbers. The thing that makes it a quadratic, of course, is that the highest exponent that you see on the variable x is 2. If you had a higher exponent on an x, then this would be a different type of polynomial, not a quadratic. So again, I know that you guys are probably already aware that the shape of the graph of a quadratic function is something that we call a parabola. It's a very symmetric shape, as you can see over here from these pictures. And a couple of different characteristics about these graphs that I want you to be sure to be familiar with, right? So whether your parabola opens up, quote unquote, or opens down, we can still always point out the vertex. So that is where your function goes from either swooping down to swooping up, or from swooping up to swooping down. It's basically where the curve changes directions and goes the other way. You could also characterize that according to this definition here. It's the very lowest point or the very highest point on these parabolas, as you can see. And then also I want you to be familiar with what we mean when we say axis of symmetry. What we're basically saying is that we have a vertical line. Here in these pictures that would be these dashed lines, and the way that we would interpret that is that this is the line that the shape of the parabola reflects over. You could say that half of the parabola looks into that mirror and sees its reflection on the other side. And so a lot of people call this the line of symmetry, or the line of reflection, or the axis of reflection. A lot of different names for the same thing. We're basically just talking about the line that we could fold the parabola onto itself over. That would be called the axis of symmetry there, okay? Really quickly, in the actual function formula, you could see that playing the role of a is either going to be a positive number or a negative number, and depending on the sign of that number, that's going to mean that your parabola is going to be opening up or it's going to be opening down. So down here, it says here that a is greater than 0. In other words, a is positive. If that's the case, then you're going to have a parabola that opens up. And of course, up here, if a is a negative number or something less than 0, then your parabola is going to be opening downward. Okay. And also, speaking in terms of the function formula, you're going to find that when we go from example to example, that there are going to be two different forms that your function formulas are going to be written in, and I would like you to be familiar with both. So talking about forms of a quadratic function, the first form is what our textbook calls standard form. You'll also see other online resources call this vertex form, and the reason that we might call it that is because just by looking at the function written in this form, we're automatically going to be able to tell what the coordinates of that vertex point are going to be simply by looking at two of the numbers that are in this function formula. So specifically, if you look at the number h and the number k as they sit in that function formula, those numbers are automatically going to be the coordinates of the vertex, again, if your quadratic is written in this form. You also see this other number in the function formula, and that's that number a. Keep in mind that's the number a that we talked about a moment ago. If a is positive, of course, that means your parabola is going to be opening up. If a is negative, then your parabola, of course, opens down. And then we could actually also go ahead and write a quick equation for what that line of reflection, or that axis of symmetry, is going to be. And that is down here. It says x is equal to h. That's the same number h from the function formula. And keep in mind that this is going to be a vertical line. So you remember Hoy and Vux from an earlier algebra class. This would, of course, be an example of a equation of a Vux, or a vertical line, undefined slope, goes through the x-axis. Okay, this would be the form of the quadratic equation that we would want to be working with, because it does tell us so much about the picture of the actual graph. So this is the form that we do prefer. Unfortunately, sometimes we do have the other form, which is something I would also like you to be familiar with. It's called general form, and it's not to say that this form does not have its uses, but this form does not tell you too much about what the actual graph looks like just by looking at the function. Okay, that is why the other form is really handy. But this form, let's say you're trying to find the x-intercepts, you can very easily do quadratic formula when the function is written in this form. But you can see down here below that there are some calculations involved if you want to figure out what your vertex and your axis of symmetry are going to be. You're basically going to have to take a look at what is playing the role of your a and b numbers here, and then do this quick calculation to figure out the x-coordinate of your vertex vertex, and then plug that into your function formula to figure out the corresponding y coordinate, okay? And then also, whatever that value is, that is going to be where you place that vertical line for your axis of symmetry. So you can see here that if the function is written in that second form, then it doesn't really tell us too much about what the graph is going to look like, at least not without some tedious calculation there. So one of the things that we might be interested in is how can we take a function written in that second form and rewrite it into that first, more preferable form, okay? Well, it turns out that there is a way to do that, and it is going to be by this process of what we have talked about earlier in the class, which is completing the square. Okay, so in this video, I'd like to kind of go back over how we complete the square with a quadratic, and that is how we're going to convert from general form to standard form. What we would also like to do is be able to go ahead and get some practice with pointing out what the vertex is and the axis of symmetry, and then also, while we're on the subject, let's go ahead and review also how we find where this parabola is going to be crossing the x-axis by finding those x-intercepts. So these are all things that the next couple of examples are going to ask us to do. So you'll see here that I've already gone ahead and done some examples for you here. We'll go ahead and take you through some of these ones that are blank here as well. But in the directions, it just basically says that, right? It says write the given function in standard form and then identify the vertex, axis of symmetry, and the x-intercepts, okay? So really quickly, in order for us to go ahead and write the given function in standard form, we're going to need to review how we complete the square. And very quickly, one of the things that we need to do before we even have the green light to perform completing the square is we're going to need to make sure that our quadratic is of this form right here. And the most important part of this form is that the number sitting in front of x squared is a positive 1. If it's not a positive 1, we're going to have to do some preliminary work in order to get that number in front of x squared to be positive 1 before we can continue, okay? And keep in mind that this is only the first two terms of the quadratic that we're dealing with when we say x squared plus bx, because what we're going to be doing when we complete the square is we're going to be introducing an entirely new term to that two terms there, and that's going to make it a perfect square for us. And that new term is going to be what we get whenever we take our b number and divide it by 2 first, and then square after that. Whatever that number is, that's the number that we'll introduce. That will complete the square, and it will allow us to go ahead and convert to that standard form that we talked about a few moments ago, okay? And also, while we're here in the directions, you can see that I've written this in green. We are going to have to find those x-intercepts, and just to remind you how you always find x-intercepts of a function, can't even talk, you always set the function equal to 0, and you solve for x. So we're going to talk about how that is done as we go from example to example here. You can see here that I've already done the first example here, but in order to take you through the process, I'm just going to go right to the next blank one here, and we're going to do this one together. So this says f of x is equal to negative x squared plus 6x minus 8, and we're going to basically go through everything. We're going to go through how we convert to standard form, and then once we do that, we'll find the vertex, axis of symmetry, and then the x-intercepts after that. Okay, so in order for us to go ahead and do this, it's going to be a lot easier for us to work with the algebra if we first replace f of x with an easier name to use. And so I'm going to give it a single variable name, like maybe say y. So I'm going to say y is equal to negative x squared plus 6x minus 8. And then, of course, we're going to go ahead and continue with our completing the square method, in which case we're going to need to go ahead and focus specifically on the first two terms of what we've got here. Because keep in mind, we're trying to go ahead and match this up to the green light form for completing the square, which is just simply positive 1 in front of x squared, and then continuing with our bx term. Okay, you can see that we don't quite have that form just yet because the number sitting in front of x squared is negative 1 instead of positive 1, and so we're going to need to do a little bit of work in order to get the green light to proceed here. So specifically here, that minus 8 that's in back, since I'm only trying to focus on the first two terms, the first step that I'm going to perform is I'm actually going to bring it over to the other side. So I'm going to add 8 because it does say minus 8 there, so using inverse operations. So on the left-hand side, I'm simply just going to write this out as y plus 8, and that is going to be equal to negative x squared plus 6x. Okay, and now I'm going to go ahead and continue to work with this by thinking about how I might work with the right-hand side to try to get a positive 1 in front of that x squared. Right now it's a negative 1. So in general, what you can do is you can take what's in front of x squared currently, and you can factor that out of every term that's on the right-hand side. So specifically, we only have 2 terms on the right-hand side, so we're just going to factor out a negative from everything on the right-hand side, so that would leave behind positive 1 x squared, which is what we wanted, and then it's going to basically change the sign on that bx term. So instead of plus 6x, we'll see here that this changes to minus 6x. And before closing off those parentheses, I am going to go ahead and leave a little bit of space because we are about to complete the square here, and we're going to need to introduce a new term. So let's go ahead and say the left-hand side there. Okay. So now we do have the form that we want. This does now look like positive 1x squared minus 6x. And now we're going to have to think about what we need to introduce. So from before, we said what we need to introduce is plus whatever that number b is divided by 2 and then squared. Okay, so we're going to take our b number, which in this case is negative 6. We're going to divide it by 2, which we can do mentally. That would be negative 3. And then we're going to square that number. So negative 3 squared is actually going to be positive 9. So in this space that I made, I'm going to go ahead and say plus 9, and that's going to complete the square for me. Okay, now here's the problem though. We basically just introduced something to the right-hand side without introducing it to the left-hand side. So we're going to need to make sure that we do that. But when we do, we're going to have to think a little bit about what it is we just introduced, okay? Because yes, what we did write down was plus 9, but we introduced it inside of this set of parentheses where everyone inside that set of parentheses was being multiplied times this negative out front. So if you think about distributing this negative back in, then what you really introduced was that plus 9, but negative 1 times plus 9. Or in other words, you introduced a minus 9 to the right-hand side. So if that's the case, then what we're going to have to make sure that we do is introduce that same thing to the left-hand side. And I know that that seems a little bit weird to have written plus 9 on the right and minus 9 on the left, but you got to keep in mind that we introduced that plus 9 inside of this set of parentheses that all had a negative out front. So we're going to have to think a little bit about what that number is that we really introduced. Okay, so that means on the left-hand side, we're going to continue to simplify this. That's y plus 8 minus 9. We could simplify that by combining the plus 8 and the minus 9 into y minus 1. And then on the right-hand side, I still have that negative out front, but now this trinomial that I've written here, x squared minus 6x plus 9, that is a perfect square trinomial, hence the name completing the square. And I can go ahead and rewrite that as a binomial squared. We've had some videos that have discussed completing the square, so I would encourage you to look back in our college algebra playlist and maybe give that one a rewatch if you forgot. But this is going to be x minus 3 quantity squared on the right-hand side. Okay, and so now I'm almost good to go. I just have one more step. I just need to go ahead and add 1 to both sides, and then instead of y in the next line, I'll go ahead and replace that with the original name for the output, which of course is f of x. I'm going to say f of x is equal to negative quantity x minus 3 squared plus 1, and there, ladies and gentlemen, is our standard form for this quadratic. Again, a lot of other mathematicians and online resources call this vertex form as well, so if you're trying to do some more research, you may go ahead and Google that, and you might find some additional information about this form, okay? But again, the reason that we wanted this form is because we can more easily match it up to the standard form, which again says f of x is equal to some number a times x minus some number h squared plus some number k, and we can immediately begin to pick out what's playing the role of a, what's playing the role of h, and what's playing the role of k by just simply comparing. So if you notice, playing the role of a, that's the number in front of your quantity squared, that here is a negative 1. Playing the role of h, again, matching up forms, it goes x minus, so playing the role of h here would simply be positive 3, and then at the very end here I see plus 1 at the end, so that means playing the role of k is positive 1, okay? And it's really important to be able to point those out because now we can immediately say that playing the role of the vertex here, again, if you have standard form, is just the point with coordinates whatever h is, and then whatever k is. And so here we figured out that playing the role of h is 3, playing the role of k is 1, so that means that our vertex automatically is the point with coordinates 3, 1. And then, of course, we can go ahead and point out our axis of symmetry, which I'm just going to go ahead and abbreviate here. Remember that that is the equation of a line. It's also a vux because it's a vertical line. So I'm going to say x is equal to whatever the number h is. And here that is going to be the number positive 3. Okay, so you can see here how quickly it goes whenever you convert to standard form, how quickly it is to find the vertex and find the axis of symmetry. They basically just fall out of the standard form whenever you convert to that, which makes it pretty handy. Okay, so the only other thing that the directions asked us to go ahead and find were the intercepts of this graph. So I'm going to go ahead and do a little bit of separating in my work here because we're now going to go ahead and find the x-intercepts. And in order to do that, we can more easily do that since we now have vertex form. We could just go ahead and take this form that we have right here, and instead of f of x, we might trade that out for 0 and then go ahead and solve this equation. Okay, now truthfully, you don't have to solve it this way. What you could do is you could go back to the original general form of the equation, and you could always use quadratic formula to go ahead and solve it, just plugging in your values of a, b, and c. That will always work. Quadratic formula is foolproof, but the reason that I may not want to do quadratic formula here is A, I have to remember quadratic formula or remember where I had it in my notes, and B, quadratic formula just has a ton of operations, and it's a lot of calculating and using the calculator or mental math, however you choose to do it. I would much prefer to do it in this way where I'm just setting my standard form equal to 0 and solving, because then I just get to use my inverse operations and I get to my answer a lot easier, okay? But to each their own, whatever you prefer to use, that is up to you, okay? So I'm going to go ahead and solve for x here by using some inverse operations. I'm going to begin that process by taking care of that +1. Using inverse operations, I'm just going to go ahead and do a quick -1 from both sides. That's going to give me -1 is equal to negative quantity x minus 3 squared. Next, if I'm trying to solve for x, I need to get rid of that negative in front of that quantity squared, so I'm going to divide both sides by -1, and on the left-hand side, -1 divided by -1, that is simply +1, and that is going to equal x minus 3 quantity squared. Next, in order to get to that x, I'm going to have to get rid of that exponent of 2 that I see on the right-hand side, and the way that we always do that is by applying a plus or minus square root to both sides. That is one of the most common mistakes that I see people making, is they may do the square root, but they may forget that plus or minus. Remember, if you're ever trying to undo an exponent of 2, you have to apply a plus or minus square root to the problem, okay? And so that's going to eliminate the exponent of 2 on the right-hand side, so I could just write whatever was inside those parentheses, x minus 3. And then on the left-hand side, I have the square root of 1. The square root of 1 is just simply 1, but it is plus or minus, so I'm going to go ahead and say here plus or minus 1. And then the last step here, I just simply need to go ahead and add 3 to both sides, and then I can get my final result, which I'll go ahead and write here by saying x is equal to, and then we would just want to go ahead and figure out what these numbers are, okay? Well, since we're working with some nice integers here, like 1 and 3, we can go ahead and use some quick mental math to go ahead and figure this out, right? So we have the plus or minus, so let's entertain both possibilities. What if we had +1 plus 3? That would give us 4. And then after that, what if we had -1 plus 3? Well, that would simply give us 2. And we end up with these two numbers here. And we actually call these the zeros of the polynomial. If we wanted to convert these to x-intercepts, then we would just have to go ahead and write these as points with coordinates. So really quickly, that would look like 4, 0, and 2, 0. But if you just wanted to go ahead and stop there by providing me with the zeros, I am perfectly fine with that, okay? So you can see here just a lot of algebraic manipulation. I can't talk in this video to achieve what we want to achieve here, but again, taking it one step at a time, just kind of reminding you of some of the previous methods that we've had for solving similar problems. These would all be things that I would expect you guys to be able to do, okay? And I've already done ahead and done the first one here, so you can go ahead and pause the screen really quickly. You'll notice that the zeros did not turn out to be so nice for us. We had to take the square root of a fraction there at the very end, so you notice that I just kind of left it in those forms. If you were curious about approximately where those points would cross the x-axis, of course, you could take those zeros and plug them into a calculator and get some decimal approximations, but here, this is fine enough to be able to just leave it in that form with the square root of 1/2 in that way. Okay, so to finish up the video here, I'm just going to go ahead and quickly do the last example in the exact same way, just so that we can say we've done a few examples in the video, and then we'll call it, okay? So again, just kind of going over that process here again, I just want to simply focus on the first two terms of my polynomial here, and you can see that I'm not quite ready to go because the number in front of x squared is not a +1, and so I'm going to do the same things as I did before. So I'm going to replace f of x with y, and then I'm going to go ahead and take that third term on the right-hand side, the -69, and I'm going to go ahead and add that to the other side, just because I'm only trying to focus on the first two terms on the right-hand side so that I prepare for completing the square. So y plus 69 is equal to 3 times x squared minus 30 times x, okay? And now, in order for us to go ahead and get the green light for completing the square, we're going to have to do something to make sure that the number in front of x squared is a +1. Right now, it's a +3. And of course, we're going to do the same exact thing that we did in the last example. We're just going to factor out whatever that number is that's sitting in front of x squared. And here, that's a 3. So I'm going to go ahead and write the leftovers as x squared minus, if you factor out a 3 from -30, that's going to leave behind -10x. And then before closing off this set of parentheses, I'm going to leave a little bit of space because we're introducing that term here in a moment. Okay, so y plus 69 on the left-hand side. So now we go ahead and continue with the completing the square step. Remember, we need to introduce the plus whatever b cut in half and squared term would be. And so playing the role of b for us is -10. If you divide that by 2, that's going to be -5. And if you square -5, of course, it's going to give you a +25. Okay, and so we're going to introduce the plus 25 in that set of parentheses. And again, we introduced that to the right-hand side, so we're going to have to make sure that we do the same thing to the left-hand side. But yet again, just like we talked about in the last example, we're going to have to be a little bit careful about what it is we actually introduced, because again, we introduced that plus 25 inside of this family that was all being multiplied times 3. So if you think about that, what we really introduced to the right-hand side is actually whatever 3 times 25 is, and if you do the math on that, that is actually 75. So for that same reason, I'm going to go ahead and add 75 over to the left-hand side here as well, okay? And so now we're just going to go ahead and rewrite the left-hand side using the simplification there. So just adding together the numbers 69 and 75, and that is going to give us 144, okay? So let's go ahead and rewrite that, y plus 144. That is going to be equal to 3 times. And again, the whole reason that we introduced that, that b divided by 2 squared term is so that we could take that trinomial and write it down as a binomial squared. And so that will be x minus 5 quantity squared. Okay? And then last step, we're just going to simply go ahead and subtract 144 from both sides, and that will finish us up here. So in place of y, I'll just go ahead and say f of x again, and that is equal to 3 times the quantity x minus 5 squared minus 144, and that will finish us up here. This is our standard form of that quadratic function. Okay, and now that we do have the standard form, we can immediately go through and pick out what the vertex is here, and also pick out what the axis of symmetry is, which again I'll just abbreviate, okay? So remember that the vertex is just whatever's playing the role of h and k in our function formula. So playing the role of h, it looks like it's positive 5. Playing the role of k, be careful with the signs in front when you compare to the standard form. That's actually a negative 144. So the coordinates of the vertex here go 5 as its x-coordinate, and then negative 144 as its y-coordinate, which seems like a pretty big number, but it's just kind of the way that we were given this quadratic formula. It's just what it turns out to be, okay? And then finally, for the axis of symmetry, remember that that is a vertical line, a vux, and so that's going to be the line with the equation x is equal to whatever the number h is, and here that's going to be 5, all right? So not too shabby at all. Next, we need to go through and find those x-intercepts. So I'm just going to go ahead and simply, just like I did in the last example, I'm going to take my function formula here, and in place of f of x, I'm going to go ahead and put in a 0, and then I'm going to set that equal to my function formula, and then use my inverse operations to solve for x here, okay? And so the first step of that, of course, would be to bring the 144 over, so we're going to add plus 144 to both sides. That's going to give us 144 on the left is equal to 3 times x minus 5 quantity squared. Just continuing to solve for x here, I'm going to divide both sides by 3. Again, just using the normal steps for getting a variable isolated in your equations, solving your equations here. I'm going to go ahead and reach for my handheld here because mental math is not my strong suit right now. So 144 divided by 3, of course, is going to give us 48. Okay, and then continuing, right? So now we have to get rid of that exponent of 2, and of course we do that by applying a plus or minus square root of both sides. And 48 is one of those numbers that a perfect square number definitely goes into 48, okay? And so while we're going to write x minus 5 on the right-hand side, we're going to need to think a little bit about the largest perfect square number that goes into 48. And I believe that that number is going to actually be 16. So we could actually break this up and say 16 times 3, in which case if we take the square root of 16 and the square root of 3, the square root of 16 is simply just 4, while the square root of 3 is something we'd have to leave under the radical. And keep in mind that's plus or minus. So we're going to say plus or minus 4 times the square root of 3 is equal to x minus 5. And then finally solving for x, we just have one more step of simply introducing a plus 5 to both sides. And so when I write out my zeros of my quadratic function, I'm going to go ahead and, since I added 5 to both sides, I'm going to start this off by saying positive 5 and then continue by saying plus or minus 4 times the square root of 3. Okay? Keep in mind those are the zeros of my, my function. We were asked for x-intercepts, so if we did want to go ahead and write down the coordinates of that, we would just have to simply go ahead and write out 5 plus 4 square roots of 3 as the x-coordinate, with 0 as the y-coordinate, and then 5 minus 4 square roots of 3 as the x-coordinate, with 0 as the y-coordinate. So those would be the two x-intercepts that we'd have here. But if you just wanted to stop there at writing zeros down, that is perfectly fine. So yet another example of going through that, using the square to convert from standard form. And then again, once we have that standard form, we're very easily able to pick out what the vertex and the axis of symmetry is, and then you always take your function and set it equal to 0 and solve for x for those x-intercepts. You can go ahead and see that part D is also sitting there for your reviewing pleasure. If you'd like to go ahead and pause the screen and just kind of read your way through that, I think that would be a really good idea. But that's all I have for this video, right? So just a brief overview of quadratic functions and how to interpret their graphs and how to do a couple of different things algebraically with quadratics. So I hope this video has been helpful to you. If you guys have any questions at all, feel free to always let me know. But thank you very much for your attention in this video, and I'll speak to you guys in the next one.